Okay, so let us start. So, hello engineers, welcome back to this ROS learning series. Today is our third session of the series, and today we are going to discuss about the different ROS related topics and what functionalities it provides. So, okay. So, a bit of recap before we move on to the session. In the first session, we had discussed about what is ROS, why we should use ROS, and some little bit components of ROS that are present in ROS that we can use to create robots. In the second session, we actually simulated the TurtleBot 3 mobile robot and uh, also learned about how what are the main components of a mobile robot, which were localization, mapping, and navigation. In today's session we are going to discuss some technical details of the ROS, how it works, and so on. Now the thing is, in the second session when we simulated the TurtleBot 3 robot, so the thing was we were using the packages that were actually developed by other developers, and they had put those packages online. Now, to completely use the full power of ROS, we can also create our own custom packages as well. In order to create those custom packages, we need to understand how ROS works and what are its different components and concepts. So that is the topic of discussion of today's session. So let's start with this. Okay, a bit of introduction to these robots. So in the top left over here, it's the dummy robot that we also discussed in the first session. On the top right, we have the UR5 robot. So this robot is a robot used for mainly research as such, and it is manufactured by the company Universal Robots, and that's where the name also comes from, Universal Robots 5. On the bottom left, we can see this is the Baxter robot. So this robot, as we can see, it has two robot arms, and it also has a kind of animated face as well. It's mainly used for industrial and research purpose as well. In the bottom right, we can see we have the Kinova Gen 3 robot. Once again, it's a robot manufactured by the company Kinova, and it's also used for research and industry purposes. Now, the point over here is that in the first session, we discussed that we wanted to build the dummy robot, and it has its various components like the vision system, the audio system, the motion planning system, and so on. Now, what ROS provides us, the components that we developed, if we develop the components for the dummy robot, these ROS packages and components should be applicable to these other robot arms as well. For instance, if we developed a motion planning algorithm for the dummy robot, then this motion planning algorithm can also be applied to the UR5 robot, the Baxter robot, or the Kinova robot. Not only robot arms, even let's say the vision system that we developed for the dummy robot, that can also be used in other robots as well, like mobile robots or self-driving cars. So what ROS provides us is that we can create components that will be reused over and over in different robots without rewriting a lot of code here and there. Right. So, okay. One benefit also ROS has is that, let's say that we have two components of this robot, let's say vision and motion planning system. So when these two components are operating, they are operating independently of each other. The vision system, whenever it will see an obstacle in front of it, then it will tell the motion planning system. The motion planning system, while it was doing its work, it will take in the message of the vision system, avoid that obstacle, and send a response to the vision system as well, like it has been avoided and you can go on to the next task. So more or less these two components are going to operate independently. So ROS uses a structure that allows it to run these components independently and also develop these components independently as well. So the concept that we use is over here. So I would like, can anyone guess which mathematical structure is this, looking at the photo? Just a guess as such. Okay. Yes, so it's a graph. This is a graph structure. Now, this graph structure is quite important for different mathematical and engineering applications. What a graph structure is composed of, it is composed of nodes and edges. These ellipses that we can see over here, these are the nodes, and the arrows that we can see over here are the edges. Now, nodes are going to represent the different components that we discussed before, and these edges, these directed arrows, are going to represent the message passing between them. It's the same as we discussed before. So, if now in the context of ROS, this graph we have over here is called a ROS graph. Now, as we discussed, these nodes are going to have the components running on them. For instance, one node is going to run the navigation system, the other node is going to be running the motion planning system, and the communication between them is going to be handled using these edges and so on. So that's how the overall architecture of ROS is. One benefit we have also over here is the plug and play part. As we discussed, now let's say we want to use a different algorithm for motion planning. What we can do is simply change the code of one node, leaving the other nodes completely unchanged. Therefore, we have a plug and play type of system where we can just directly put a new code and the rest of the system remains intact. We don't have to change anything else. So that's the power that this graph structure provides us. Okay, let's see this in action. So I already have this ROS running over here. Now what we will do is let's just launch the Turtlebot 3 navigation example that we did in the previous session. So let's try that. So I'm starting the simulation over here, and in the other terminal, I'll just start the navigation example also. Okay, so everything is running now. Now we are going to type this command over here. I'll just zoom in. ROS node list. And when we run this command, this is going to show all the different nodes that are currently running in this example. Now let's discuss these a little bit. For instance, the gazebo and the gazebo GUI over here, they are responsible for running the gazebo. This means that gazebo is running on one of the nodes of that ROS graph. We have this map server over here. The map server is responsible for displaying the map that we had. It's just, yeah, it's responsible for handling the map related functions. This AMCL over here is the localization algorithm. Now, AMCL stands for Adaptive Monte Carlo Localization. It's a localization algorithm that is running as a separate node in this ROS graph. In the move base is the navigation stack of ROS that we are running. It is also running on a separate node. Robot state publisher is just telling us the location and the state of the robot joints. ROS out is responsible for logging the different errors and warnings that we see. There is a separate node for that. And there is also a node for RWiz, which is responsible for the visualization, the RWiz window that we also saw. So we can see that the nodes are actually working over here. Right. So we saw that the nodes are actually working over here. Now let's proceed further with this. I'll close the simulation as well since it seems to be quite heavy. Okay. Now let's discuss how do we run these different nodes. We just saw that we typed ROS launch command and it actually launched a number of different nodes. How do we actually run these nodes? So the function that or the command that we use to run a single node is ROS run. Now these are the template instructions that we can use for this ROS run command. The first one is ROS run package name, file name, parameters. So the first one is useful when we have installed a package from the user sudo apt-get install command. In this case, we only know the package name. We are going to type the ROS package name and then we are going to write the file name. In addition to that, we can also add the different parameters. As an example, the one we did in the map saving part in the previous session, that we ran ROS run map server map saver. So map server is the package name and map saver is the binary executable. Now, the nodes that are running in the ROS, they are actually code files. In a sense, they are code files. These code files are either written in Python or C++. So if we had a C++, this map saver over here, it's a binary that is compiled from the C++ code. And that is what's running over here. And also we are also adding the parameter over here as well towards the end to where to save the map that we have. In the first command as well, we are running ROS run. We are taking the package rwis and we are starting its executable rwis. Same, it's a C++ code that has been compiled in binary that we are running. The same command works for Python files as well, but most of the applications that are pre-built in ROS, they are usually built in C++. Python files are mostly custom ones as such. So another way to run a single node is ROS run file name and parameters. Now this is useful when we have we know the exact location of the file that we want to run. If we know that, then we can use the second command. If we don't know and we just know the package name, we can use the upper command. Now this will only run a single node, as we can see. So there is another way of running the nodes that we have. Now, I would like to ask a question over here. We can run single nodes, that is good enough. So why would we need another method to run the nodes as well? Any guess related to that? Okay, so so the reason why we need another method to run the different nodes is that when we run a node, it's only going to run on a single terminal. If for our application, like we saw in the screen on the running the ROS example as well, that there were 6 different nodes. Now it is quite cumbersome. We can say that we open 6 different terminals and we launch each and every node one by one. So this is exhaustive way to run all the different nodes. What if we have in our application 10 or 20 nodes, then we would have to run 20 different terminal windows to run them. So a better way to run them is using launch files, which is the next command. So ROS launch is the command that is used to run the launch file. What launch file is? A launch file is simply an XML based file that is used to automate the execution of the different nodes. So the template that we use to run this command is ROS launch. It's very similar to ROS run, package name, file name, and the parameters that we want to change. If we know the exact location of the launch file, then it's simply ROS launch file name parameters. Now in the previous session as well, in all the sessions that we have discussed, that we have a ROS launch command that runs a, now this first thing that we can see over here is the package, turtlebot3 slam is the package. And the last part over here is the .launch file. So it's taking the turtlebot3 slam.launch file from the turtlebot3 slam package and running that. And that is automatically starting the different nodes that we have. So for an example, let's say that we want to check like what is the code that is present in the turtlebot3 slam. So let's first go and check that. I'm just simply opening the turtlebot3 package on GitHub and we can see the code over there. So we have turtlebot 3 slam. We are going to go in this package, and then we are going to this launch folder. In the launch folder, we have turtlebot 3 slam.launch file. I'll zoom in. Okay, so these are the different parameters that we had. So as over here, we were adding the parameter slam methods equals G mapping. So over here, we can also see that there is a parameter slam methods, which by default is set to G mapping. But if we want to use some other algorithm, we can use that as well, like the cartographer, Hector, Carto, frontier exploration, and so on. So these are the different parameters that we can set. Okay. And this is the how a single node is launched using a launch file. As we can see, this is launching the RWiz node of the application. So this is going to run the RWiz. Another thing that we can note is that a launch file can launch other launch files as well. So as we can see over here, this launch file is launching this other launch file that goes by the name turtlebot3 underscore whatever the parameter that we provided for slam methods dot launch. So for our example, we provided G mapping. So it's going to further launch turtlebot3 G mapping dot launch. Let's see what that launch file also contains. So there are different parameters that can be set, and we are now launching the G mapping node. So this is going to launch the G mapping node. Other than that, there is also another launch file that it is further launching, which is turtlebot remote.launch. Let's not go into that. So just to give a basic idea that launch files are responsible for launching other launch files as well as launching the nodes. In this way, we can run a big number of nodes by just writing a single launch file. So that's the power it provides. Okay, so this is all the things that we had to discuss for the nodes part. Now what we have to discuss next is the communication between them. So if you have any questions related to the nodes that we discussed till this part, so you can ask them now. Then we will move on to the communication part as well, how the different nodes communicate with each other. Okay, so no questions as such. All right, so for communication between the different nodes, ROS provides us with mainly 3 different communication systems. The first one is the publisher subscriber, second is the services, and third is the actions. Now the publisher subscriber type of communication is the most used one, and we are also going to discuss that in detail much. The services and actions are mainly used in big ROS projects, and for simple projects, the services and actions are not used that much. So we're just going to discuss them in brief, how they work and so on. So let's first start with the publisher and subscriber. Okay, so the publisher and subscriber, now the ROS communication types, they are a little bit difficult to understand at first, but as we keep on using these ROS components, we get to know about them a little bit better. So let's understand this using an example. So if you have seen the movie Ratatouille, these are the 2 characters from that movie. The left one is Mustafa. He's a waiter at a restaurant, and Remy is the chef. So the Ratatouille movie is about this rat Remy that wants to become a chef. So Remy is the chef that works in the restaurant, and Mustafa is the waiter that takes the different orders and tells them to Remy to start preparing them. Now the thing is, Remy is such a good chef that once he starts preparing a dish, then it would not be good to disturb him. So while he's preparing the dish, he will complete the dish and then he will return to take the next order. However, when Mustafa is taking the orders, he has to go and tell Remy that the next order he has to prepare is this. Also, it can also be a case that once Remy has completed his dish, then he wants to take the next order and Mustafa is not available. He's already taking another order, or he is delivering the other order. So what they do is they set up a communication system of how they can communicate with each other at different orders. First thing they do is set up a blackboard at a place and declare, or they both decide that they will write orders on this blackboard. So what Mustafa will do, whenever he gets an order, he will write that order on that blackboard. And then he will go on to do his other work like serving the dishes or taking the next order. While Remy, when he is preparing, all he has to do once he has prepared his dish, he will come back to the blackboard. He will check what is the next order, erase it or strike a line through it, and then start preparing the next order. Now, in this way, both of these characters are able to perform their work while they are not actually depending on each other, that the other will bring the message and then they will start cooking and so on. So the publisher subscriber mechanism also works in a similar way to this, where the different components are going to work independently of each other. Whenever there is a message, that's going to be in a buffer like kind of thing, and it's going to be read. So now let's discuss it in more detail. So for the publisher subscriber, there are two components, the publisher and the subscriber. So the first thing that when these two nodes want to communicate using this, that they set up a topic. So a topic is it's a ROS structure that we can say. It's a ROS concept. It's just a theoretical type of concept that we will also see in the running of ROS. So just like the blackboard that we set over there, we set up a topic. Now, on this topic, only particular type of messages can be sent. We have already declared at the start what kind of messages we want to send. Let's say we want to send an image through this topic, then we cannot send any number or anything else through this topic. So first thing is to set up what this topic is going to pass the message of. Then whenever the publisher is ready to, whenever the publisher is working and when it has generated its message, it's going to publish that message on this topic. And whenever the subscriber is ready to receive any message, it's going to read from this topic the message that the publisher provided. So that's how the communication is working, very similar to the example that we discussed. Now, one thing to note over here is that since these two are performing independently of each other, so let's say the publisher is quite fast compared to the subscriber. So the publisher is publishing the messages to the topics very quickly. However, the subscriber is a little bit slow and it reads the messages slowly as compared to publisher. So there may be a case that the subscriber is reading, the subscriber is missing some of the messages that the publisher sent. And this is normal to happen because we want the two nodes to run independently of each other. A similar case can also arise for the subscriber, for the other way around as well, that the subscriber is reading the messages quite quickly compared to the publisher. So it may also happen that the subscriber will read the same messages one or two times or many times as such. And this is also completely normal to happen. Why we want this is because if the subscriber or the publisher is a slow computation node, then we do not want the other node to also take the same amount of time. If it is a fast node, then it can perform quickly. If it is a slow node, it can take its time to run. So that's the reason why it is okay to have this kind of communication as such. So I hope you understood that. All right, so now let us try to see it in action, like how we have this in the working system. Okay, so first we are going to launch the simulation, the Turtlebot 3 simulation. So it's running now. Now the command that we will type over here is ROS topic list. So this command will list all the different topics that are currently available. As we can see over here, we have CMD well, clock, gazebo, different gazebo topics, odom, scan, and so on. So the next thing that we will discuss over here is, okay. Now, as we discussed that the topic is going to contain a particular type of message. Now, two important topics that we are going to discuss in detail are the CMD well and the scan. So as we discussed before as well, that the Turtlebot 3 has a LiDAR sensor on top of it. So it's basically a laser sensor that takes in the range of the environment and returns us the value of how far an object or obstacle is from the robot. So let's first check what this scan topic actually contains. So to get more information about this scan topic, we are going to type this command ROS topic info/scan. So it returns us the information about this scan topic. As we can see that this scan topic currently has no subscriber. However, it has a publisher which is Gazebo. So this is quite normal to expect that the Gazebo simulation is going to return us the scan messages that we have. This type thing over here is sensor messages/laser scan. It's just a data structure to define how the message should be formatted, like what it should contain, what should be the header values, how the data should be formatted, and so on. So this is just a for making the messages consistent so that different nodes do not pass this information in different ways. Everything is consistent. That is why this type is used. That's for the scan. Okay, let's also see what is the ROS topic info for CMD well. Okay, now we can see that it has a different type which goes by the name geometry messages/twist. It has no publisher, but it has a subscriber which is Gazebo. Now, CMD well is responsible for the motor speeds, we can say. If we provide the CMD well with the value of a motor speed, then based on that motor speed, in the simulation, we are going to see the Turtlebot 3 move at that particular speed. That is why Gazebo is a subscriber over here, as it wants to read the message that is coming from other publisher that is telling them the speed of the motor. However, in the case of scan, the Gazebo is the one that is publishing the information regarding the laser messages, and we want someone to read those messages as an input. So that's that. Okay. So next thing is, let's now see what is the actual message that is coming through the scan topic. For that, we are going to type ROS topic echo/scan. I'll just go to the first message and then I'll explain what it is. Okay. So here is the thing. Once I typed in ROS topic echo/scan, then we can see that we have the header over here. And then we also have parameters called the angle, minimum angle, maximum angle, increment angle, minimum range, maximum range, and the different sensor values in this list of ranges, as we can see over here. The first few are infinity, then we have 3.06, 3.05, and so on. Now, once we type this command, since Gazebo is continually doing this computation of the laser messages, we are going to continually receive the messages from the scan topic. That's why we had a lot of different messages that were coming over here. As we can see, they are being repeated as Gazebo is sending them. We are receiving them one by one over here. That's why all the different messages. So this is how it's, so the things that we discussed are actually how it is working on the ROS real-time system as well. Okay. So if we, okay, so this is the thing. Now let's discuss an example related to this. Now let's say that we want to create a robot like this that will just keep on moving. Now to create this, we actually only need two components that we discussed before. First, we need the scan, and the second we need is the CMD well. Now the CMD well will be sending the motor commands to the robot, and the scan will be responsible for the object avoidance that we can see over here. As we see, it does not collide with an object, it just detects it and then moves in other direction. So let's see how we can write this. Now the code that I have written for this is in Python, and if you don't understand the code, that is also completely fine, since the main objective of this showing this code is that how we can create custom ROS packages as well. So let's open this. Okay. I'll just magnify it so it is visible clearly. Okay. Okay. All right. So in the start, we are, as we saw before, we are importing the different message types. First, we are importing the twist that is responsible for sending messages to CMD well. And then we are importing the laser scan, which is responsible for getting messages from the laser. Now, as we can see over here, we are first initializing the node. So the node that we are running over here is WonderBot, and we are then creating a subscriber for the scan topic, and we're creating a publisher for the CMD well topic. And now over here below, we have just wrote the logic for how the robot should behave. Now the robot should go straight for some time interval. Then after some time has passed, then it's going to rotate and go in another direction. However, while moving forward, if the time has not yet expired for going forward and the robot encounters an obstacle, then also it is going to stop and then rotate as well. So to read the scan messages, we can see that we have this function over here, scan callback. We are taking the ranges part of the message. As we saw before, ranges contain the different laser values. We are taking that ranges, we are calculating the minimum and then returning and then saving it in a global variable. Now to send the messages to the robot, the motor messages, we are first declaring this twist object. Then we are assigning a linear velocity to the robot, 0.1. And if we are rotating, then we are providing an angular velocity of 0.1 to the robot. And once we have created this message, we are publishing that message as well. And this rate dot sleep is just to maintain a rate, like we want to run the ROS, this node, about 10 hertz, which is 100 millis with a time period of 100 milliseconds. So this rate dot sleep is just responsible for that. So that's that. Now let's try to run this code as such. So to run that, we can use the ROS run command, wonderbot.py. Since we know the location, therefore we can type this as well. However, this is one way to run it. Another way to run it as well is just simply using the Python command, which is a command that I usually prefer. Now, although both the commands would work similarly as such, so once it is running, the robot will start to move over here as well. So it's a little bit slow on my computer since the load is quite too much. So it's moving forward, and once it detects or the time has expired, it's going to rotate again and then keep on moving. Now, while it is running, let's just run the ROS topic info command that we ran before as well on the /scan. So now we can see that not only it has a publisher gazebo, it also has a subscriber Wonderbot, which is the node for the code that we wrote. So we can see that the Wonderbot node is reading messages from the scan topic, and then it's using that scan topic to write it on CMD well. So let's do that for CMD well as well to see what changes over here has taken place. We can see that for the publishers, the Wonderbot node is over here. So that is publishing messages to this topic. And we can see that the robot is still moving and it will just keep on moving as such. So let's stop this and move on to the next part. Okay. So this is all for the publisher subscriber. Okay, I'll stop Gazebo as well since it. All right, so this is it for the topics and publisher subscriber based communication. If you have any questions related to that, you can ask them as well. And then we will, after that, we will start the services and then we will go on to the actions part. Okay, so let's move on to the next part, which is the services. Now, services implement more like a client server kind of mechanism of communication. Now, a server is simply someone that wants some, that sends a message, which is also called a request to the server. The server is going to process that request. And once it has processed that request, it will send a response back to that client. So this is how the client server communication takes place. In this case, the client, once the client sends a request to the server, the client has to stop its communication, stop its computations. The client will simply stop running its code until it receives a response from the server. Once it receives a response from the server, then it's going to continue its execution that it had. So this is how the client server communication takes place. It's a now, a technical term related to this waiting thing that we had is called synchronous communication. So it waits until it receives a response. So that's how the service communication takes place. Let's see that in action as well. Let's again run the simulation. And for to see the different services that are being published, we type in the ROS service command and we're going to type in ROS service list. So let's wait for this simulation to come up. Okay, let's type in ROS service list. All right, so we can see there are a lot of different services over here and we cannot see them in one single scroll. So over here we can see what common thing that we can see that most of the services are from Gazebo, like apply, body range, and so on. I'll just explain some simple ones from over here, like the Gazebo reset simulation. It's going to reset the simulation as we can clearly read from over here. The pause physics is going to pause the Gazebo. It's going to pause the simulation, and resume physics is another service that is going to resume the computations of the simulation. So we can see that mostly the services are mostly available for Gazebo as such. We do not have many services related to other different nodes as such. There are some from ROS out, but most of them are from Gazebo for stopping, resetting, and changing some parameters of the simulation. So that's how it is. Okay, now let's discuss about actions. Okay, now the action is a little bit elaborate compared to services and publisher subscriber based communication. In an action, the It's quite similar to how the client server communication takes place, but in action, the client will not wait for the server to complete its execution. Once a client sends a message to the server, it's going to keep on doing its computation. And once the server has completed the computation, it's going to send a message to just tell the client that the work has been done and you can do it accordingly as such that you want to do. So how it works is that once the action client sends a request to the server, then the different information from regarding that task that was sent are published through different topics, like the feedback topic over here. And once the request has been completed, then a response is sent to the client to notify that the work has been done. Now, a technical term related to this communication where it is not waiting for the server to respond is called asynchronous communication. Let's again see this in action in over here. So we already have the simulation running. Now we are going to launch the navigation launch file. And one important thing is, just like we had a separate command for ROS service, we do not have any separate command for action-based mechanism. For that, the action mechanism is implemented on the topic publisher subscriber based communication. So the way to see the different things published is through ROS topic list that we saw before as well. Type the command ROS topic list and we are going to see the different topics. So a particular set of these are responsible for the action communication, like the move base cancel, move base current goal, move base feedback, move base goal, move base result. Now I'll just close them since I have a screenshot of them over here and we will see further from here. So just to show that they are actually working in real time as well. I'm just going to stop everything. Then we'll go to the slides. Okay, so now the move base cancel is responsible for canceling the task that we gave to the server. Let's say that in middle of its execution, the client decides that the task that it sent to the server was not worth it, and it doesn't want to complete the execution for that. Then it's going to call this cancel topic, publish to this cancel topic to stop the computation of the server. Current goal is simply the current task that has been provided. Feedback is just a feedback of how the task is going on, like how much percentage of work has been completed and so on. Goal is to tell the next task that what it wants to do. Result is the one that is responsible for telling after the task has been completed, it tells through the result topic over here. Status is also somewhat similar. Now the thing is, now the difference between actual service and action is where we use them is that services are mainly used for tasks where the computation is quite less and we know that the task is going to complete very quickly. For instance, in Gazebo, when we want to pause the simulation, we are quite sure of that it's not going to take a lot of time. Once it has completed, it tells us that the simulation has stopped. That's how it works. Actions are mostly used for long running tasks, the tasks that are going to take a long amount of time. For instance, now why action based communication is used in the navigation, that once we send a goal to the robot that it has to go over there, now it's a long running task that it will take a lot of time to move from one point to the other point. In the middle, if the client decides that it does not want to move the robot to that location, then it can cancel as well. And while it is working, it can receive feedback from it as well. So that's what the main difference between where the both of these are used. As I also said before, that these are mostly used for big ROS projects, not for small ones. For small ones, usually the publisher subscriber based communication is used. Okay, so all right. So this is, I think that was for this session as well. We have discussed how the different nodes are working and how the communication between them also happens. And since this session was mostly theoretical and conceptual, the uh, posting assignment for this is also optional. If you want, you can post anything related to that. It's completely your choice. If you don't want to post, it's also completely fine. In the next session, we will be simulating the UR5 robot. So this is a robot arm. For in the second session, we simulated a mobile robot. In the next session, we will be simulating a robot arm. So that's for the next session, and that's all for this session as well. If you have any questions, you can ask as well. So then- okay, so Aman asks a question. Okay, so you are making a drone that is using stereo camera and you want to integrate SLAM for that. So what's the actual problem? Like it's mostly all the information is mostly available on the internet. You have to just try to see how you are going to make this work for the drone. You can use the ROS packages that already have been provided. The thing that you have to try is using integrating it with hardware. So hardware integration is a bit trial and error kind of thing that you have to see what is working and what's not working. Yes, Jetson Nano would be good for the computation, as Slam is a bit compute intensive, so Jetson Nano would be good. So I would suggest, I think you need to read about it on the, now this, the project that you're doing. I've seen people do this for mobile robots as such. So it's a quite, mm, people have done this project. So you can get a lot of information about this from the internet as well. I'm not seen for drones, but for mobile robots, this has been done. So you can use the resources for that. And I think I know a repository for this as well. If I get it, I'll share it on the classroom as well. You can have a look for that. That's mostly for mobile. That I think it is the same that they are using Slam, but it's for a mobile robot. So I think you can have a look to see how it is working. Okay. Yes, that would be. So for the stereo camera, either you have to. So I'm confused in how I can do it. Okay. So I will try to find the link to that and share it as well. So for also myself, I haven't actually worked with real robots, so can't surely say about what you can do, but I'll share the links regarding how it can be done. So you can have a look at that. Okay, so no questions. I think we can close.